Okay, let's go ahead and get started. So last time we saw how to create your kind of your basic Java visitor based recipe that's going to come in and it's going to use a Java visitor to modify a Java source file. It's going to use sorry, at least I still have some I did clear my throat. Okay, so yeah, last time we saw how to the kind of went through the anatomy of the assert equals to assert that recipe, covering the basics of how a a refactoring visitor uh, based on manipulating a Java source file is typically put together with visit method invocation being overridden. We used a method matcher to check that the method invocation was of the type we were interested in, manipulated some imports, and ultimately used Java template to manipulate and change the LST to produce the desired result. And we tested it all with the rewrite test interface that is provided for JUnit 5. Now that I think about it, it would also work for JUnit 4 and other test frameworks, but we just typically use it with JUnit 5. Okay, so since we've kind of covered your basic editing visitor, this time we're going to get into some more advanced features of the framework. And one I want to show you, begin by demonstrating perhaps, is data tables. And data tables are user-defined. Let's just get a browser window over here so I can show you. Are are recipe-defined tabular data that a recipe can extract from the source files it runs on in order to present that information and make it accessible to business analysis or business intelligence tools of your choice. I know that the open source Maven plugin has been updated to output data tables. I'm not sure if the open source Gradle plugin has or not, but if not, someone can go and add that pretty quick. So let's look at a recipe that produces a data table so that we kind of see what sort of thing we're talking about in action here. So this is the find and fix vulnerable dependencies recipe, which is a popular one. This goes and compares all of the dependencies in your code to the GitHub Security Advisory database, which is a superset of the National Vulnerability Database, which is the origin and source of truth for those CVE numbers that we all know and love. And this guy, like most recipes, will attempt to suggest changes to you, right? If it notices that the dependencies that are in use um, have entries in the vulnerability database and that you're only a patch version away from being on a non-vulnerable version of that dependency, then it will try to update your build.gradle or your Maven POM accordingly. But it also records information on all of the vulnerabilities that it notices, not just the ones where it suggests fixes. And so if we go to the cancel the rest of this run so we can go right to the results, it also produces a variety of data tables. Now, there's a couple data tables that every recipe produces. Source files that had results is just a listing of the source files that were modified by the recipe. Source files that had errors only shows up if there were some errors running it, so that's something for me to look into later. Then recipe performance can be used to see how long each recipe that was involved in a composite spent on any given source file, so that you can identify when your recipe is slow, which of the component recipes within it were the slow ones that need to be optimized and improved. So here, but most interestingly, there are any other data tables that are produced, those that come from that are specific to the recipe itself. And so this guy produces the vulnerability report produces this vulnerability report data table. And if we go and embiggen these columns, we'll kind of see what kind of information we're working with here. Now, the first 5 columns are added by the framework to any row that you produce, and this just goes back to what repository this guy was running on. You know, the origin, the branch, all of that good stuff. And afterwards, we get into all of the specific stuff the stuff's unique to this recipe that it produced as part of running. And so in the case of this guy, which is about security vulnerabilities, it notes the CVE number, the GAV or the GitHub Security Advisory number. It notes the GAV coordinates of the potentially vulnerable dependency, and if there's a fixed version available, they the version of the fix is noted here. So you know this is where we get the information to note that, hey, you know, if the fixed version is only a patch version bump away from the version you're on, it should be pretty safe to go ahead and upgrade you. So the delta between these 2 versions is what this recipe happens to use to decide whether or not it should suggest a change. Since, you know, we could otherwise it would just be, you know, a recipe that blindly bumped you to the current latest version of everything, even if that was a major version bump, and likely to result in breaking compilation and tests and all that stuff. Okay, so that's kind of the concept of a data table. And on top of these data tables, we like to build data visualizations, like this guy, which is a Jupyter notebook. Now, there isn't any way or there, I won't say there isn't any way, there isn't anything built into the open source like Gradle or Maven plugins, or even our proprietary CLI, which makes it easy to produce visualizations just like as part of the recipe execution process. But these are all based on Jupyter notebooks. So, which is a widely used and well-known technology for doing data analysis and visualization in Python. So if suppose I'm just pointing out that if you're so inclined, you can use Jupyter notebooks to further analyze and visualize the data that is produced in your data tables. But of course, you can use any other business intelligence or data analysis tool that you like as well. You know, Excel, Power BI, Tableau, all that good stuff. Yeah, so that's kind of the concept of a data table. Let's look at creating one ourselves. So we'll get started on that. Going back to our rewrite recipe starter project, which you may already remember from last time. And the recipe I'm going to live code today, the final version of that is in that project. So if any time after this presentation you want to check that out, then I encourage you to do so. So let's see. So for the recipe, we will create and its custom data table. Let's go ahead and get started. So let's make what we'll have this recipe collect and produce a data table of is class hierarchy. So recording when a class extends another class or has or implements an interface. So the raw data that you would need to use to start building a map of your project's, you know, polymorphic relations. So let's see, we'll call this class hierarchy. See if I spell hierarchy correctly. That looks right. Extends recipe. Oh, I should make this bigger. There we go. Slap those Lombok annotations on there. There we go. So class hierarchy report. Spell hierarchy correctly the first time and not the second time. produces a data table listing class inheritance relationships. And just like so we're not really particularly planning for this guy to make any changes to source files, just extract information into a data table. So let's override get visitor and then stop here for now while we go get the data table that we're going to write to set up and go get a test case set up to exercise it. So by convention, we tend to put the data table implementations themselves in a package, in a .table package. So I'll create a class hierarchy report type in order to contain the data. And here we go. And the first thing I'm going to do is I'm going to define a row type that that contains all of the custom data that we want this recipe to collect. And so to start with, we're going to collect the name of a class and the name of the class it extends. And we'll call this superclass name. And we shall place these column annotations so that we know what column headings to put there. I'll specify this is the fully qualified name of the class. Oops, not current. Yep, there we go. And the last thing to do is to make this class hierarchy report type we're creating extend the data table class. And I did that after the row, or after defining the row type, because this guy wants to be parameterized with the type of row that this table is made from. And it's going to complain that you need to have a constructor. And so in here, what we're going to do is we're going to, the parameter that needs to be passed in is the recipe producing this. And then we're going to provide the metadata that if you saw in the user interface, where'd it go? We saw in, not Discord. No, not that. When we saw in the user interface earlier that we had a name and a description for the data table, this is where that would come from. Now, so there we go. So we have our data table type. Now it's time to create the recipe that is going to populate a data table with this information. And we should create a test case to exercise this. Yeah, so we'll make a class hierarchy test. Zoom that in. We're going to implement rewrite test, just like we would for any other test. And we could override the defaults method from rewrite test, which, as you may remember from my explanation last time, allows you to configure any common configuration to the test cases. And in every case, in every test case in this class, we're going to be testing the class hierarchy recipe. So that's all we got to do. And make a JUnit test method. In here, we're going to run our recipe as specified in the defaults method. And the most basic thing we can do, I'll import that. We'll do a static import for this so it looks good. And maybe give IntelliJ a hint that it can syntax highlight this. And boom, class A. So we would expect that running the recipe on this class would produce a data table with one entry that says that A exists and it extends java.lang.object. So how do we write an assertion about the contents of a data table, because a data table isn't reflected in the in a diff or anything, so we can't just put another argument here. Instead, you can, in this optional first method, or optional first argument to the rewrite run method, you could specify a recipe spec to configure various things about how this test should work. You can, for example, override the recipe. Like if you wanted to have something different from the defaults method, all of the same options are available on the spec here. If you wanted to, make other assertions about it that are about the result of the recipe run, they could be configured here. And in this case, what we're really interested in is this data table function. And this allows us to assert that the recipe running on this source file will produce a data table with the contents we expect. So this guy hire report.row.class, and this guy is the note that this is not the type of the data table, but the type of the row within the data table. So if you are writing a test and confused why this function isn't working, check that you're giving this first argument the type of a row, not the type of the data table itself. And then we get this, could provide a lambda, where the rows object is going to be passed in, and we can make assertions about its contents. So we can assert that using, we like to use aspect for J, not aspect for J, assert J, that's the one. We like to use assert J assertions. So if you're paying attention to the recipe we made in the basic session, this will already look familiar to you, this kind of fluent style of assertion. When working with a collection, you can use this contains exactly function to say that this list of rows is going to contain exactly this entry in exactly this order. So now we have our class and our test setup, and we're all ready to implement our recipe. So we can go to the class hierarchy recipe and return from get visitor a new Java ISO visitor. And if you remember our, this recipe, the last recipe we wrote concerned itself primarily with method invocations. This recipe concerns itself primarily with class declarations. So it follows that the class declaration that we're going to, or it follows the visit class declaration is what we're going to override in here. So to start typing visit class declaration, and it pops up for me. Very good. And you may remember how important it is to do traversal into sub elements of the LST element you're visiting, particularly in a case like this where inner classes exist. So if we did not, if we don't have this traversal into, we don't have this traversal into the sub elements of this class declaration, our report would be incomplete for any code base that contained inner classes or inline class declarations of any kind. So I'm going to accept IntelliJ suggestion to move this to a local variable. And now we can get the information we're interested in off of this class declaration. And in particular, off its type information and metadata. So this is a place where maybe let's hit this in the debugger and take a look at what's on this object so that we can make this apparent. So if I look at this class declaration variable in the debugger, I just want to point out that in the LST itself, the part that represents the syntax of the file, we could go look at the extendings, right? And that would be populated if we had said in the test, if this extends something else, right? Then this extendings field would have something in it. But it doesn't because there isn't anything here. But it is implicit within Java that A extends java.lang.object. So we would miss the relationship between A and object if we just looked at what was there in the syntax. But the metadata does not lie. And if we instead look at the type that's on this object, we see that there's a Java type.class representing it. And this Java type.class object has a variety of other information, right? It notes that the super type is java.lang.object, and it also notes any modifiers on this class type. It notes that there's an owning class, an outer class around it. It notices that there's interfaces, members, and it even keeps track of what methods are available on this object. In this case, there's just a constructor and anything it might inherit from object. So when you look at this, at the type information here in this metadata, it is, richer or more comprehensive in a way that the syntax alone doesn't allow for. And this is one reason, like the complexity of putting together the type metadata is one of several reasons to use something like Java template to construct your LST elements rather than doing it by hand. Because if you, hand construct your own type metadata, well, there's just a lot of stuff in here, right? And some of it is circular, right? Because we have even the list of methods that are defined on the class, and the methods have a reference to the class that declares them. So this is, most of the LST is a tree. It is directed, it is acyclic, and that makes it easier to work with. But there's no expectation that the type metadata be acyclic. Java lang object refers to itself in its own definitions many times, and it refers to string, and string refers to object. So the type information can be a tangled mess, but it's comprehensive, it's correct, it's what you as a human programmer would expect. So we can look at the type information. We could say we can get the type. And there's always a possibility that the type information could be null. And this is this is the case if we failed to type attribute something, which in the context of Java would only really happen if the if something was missing in the class path. And I don't know how it would get to the point of producing a full Java LST if something was missing, because we do parsing after compilation. So it probably would have failed to even begin parsing if there was missing type attribution in Java. But because the JLST is shared by several languages, this visitor as written may also end up running on Ruby scripts or Kotlin scripts or other JVM languages. And if you were running on a build.gradle file, it would be much less surprising for there to be symbols without type attribution. So anywhere that the API, the OpenRewrite API notes that something is nullable, believe it. If a field is marked as nullable, there is a circumstance in real code that you will encounter where where that value actually is null. And so, if we were to, I don't know, do something with this. If we do something like this, IntelliJ, because we use these nullability annotations, IntelliJ will try to warn you, and I believe Eclipse will as well, although I haven't checked. So, let me know if I'm wrong about that. But it will tell you that this may produce a null pointer exception. So if you're writing recipes and you're getting the yellow squigglies below your symbols, you're going to run into null pointer exceptions. if you're in the habit of ignoring warnings, at least pay attention to those, because this will legitimately save you time and trouble in your recipe authoring and execution. Okay, so now if we've made it to this line, we have the type information, and we need to actually put it in the data table. And so the way we usually represent data tables is with a field on the class, and we tend to mark these fields as transient, which may be a little bit strange, because you might say to me, Sam, that's ridiculous. I've read through the entire recipe scheduler. There's nothing multi-threaded in there. Recipe execution parsing is single-threaded, well, except in maybe in the internal implementation details of the parsers, but basically everything in OpenRewrite happens on a single thread. Why are you marking this transient? That is partially so that this doesn't get serialized along with the recipe class, so that we note to when the recipe itself is serialized or deserialized from YAML, that this should not be serialized with it, and that Lombok annotations should not include make constructor parameters for these guys. We're kind of saying that, yeah, even if there isn't like multi-threaded transients to worry about, that this guy should be treated as something akin to a cache. So that's why we tend to mark it as transient, even though this is all a single-threaded process. Okay, so now that we have that field established, we can write stuff to it. So we could say report.insert row, and the first parameter is insert row is the execution context, which is where the data will actually be stored, because you'll note in their definition of this object, class hierarchy report is actually kind of stateless. So if we're talking about inserting a row, well, it's actually the place it's actually going to be stored is in the execution context. And if you've never looked or really thought about the execution context before, maybe this is a good time to mention it. But the execution context, which is passed through this whole process, it is basically just a map of string to object, and messages can be put in here that are available for the entire recipe execution process. So this is used for a whole variety of purposes. Recipe authors don't tend to need to add messages to the execution context very often. If you are passing state around between source files, a scanning recipe is a better way of dealing with that. And we'll kind of show off scanning recipes next. So if you are writing information to the execution context during your recipe run, well, that would just know that would look a little bit suspicious to me. I would wonder why you were doing that and think that there would probably be a more appropriate mechanism for passing state around than the execution context. But this is how utilities of various kinds can be made available to a recipe. Things like recipes that need to do dependency resolution, that need to do HTTP requests or network requests of some kind. The execution context can be used to store, hey, this is the appropriate HTTP sender implementation to use. And that lets us do things like, on the SAS, where the use an HTTP sender that knows to deal with the network configuration of the context the SAS is running in. And if you're running a recipe locally, it could just use a basic HTTP sender, or you could configure, one to use your corporate proxy or whatever. So that's kind of what the execution context is. And because it does just have this map of arbitrary data within it, that is actually the place where data table rows get stored. I suppose you didn't really need to know any of those implementation details, but since you've gone to the trouble of coming to this presentation, I figure you must be a curious sort. And man, I really stabbed myself in the foot by naming this class hierarchy, because this word hierarchy is just kind of hard to spell. I find myself having to struggle to spell it every single time I write it. Okay, So now we're inserting a row into the execution context of the type of this particular report. We have the type information off our class declaration, so we can start writing stuff out. Right, type, get fully qualified name. And so there we have our class name and our super type name. And this is a situation where, super type can be null, but at least in the context of Java, the super type is only ever actually null if it's java.lang.object you're looking at. So this is a pretty safe potential null pointer exception to ignore, right after I just cautioned that that you should never totally ignore a null pointer except a nullability warning coming from the API. So, out of an abundance of caution, we can use a ternary operator here to do something. So we can just say if the super type is null, we'll just do the empty string. Don't actually expect that to come up, but running in, if this were to run in a language other than Java, might have some unexpected result. Okay, so now that we have implemented our recipe, let's try running this test. And see that it passes. And it does. That's good. I did not forget how to write this basic recipe. Yeah, and you can see that if you want to hit a breakpoint in the test, you see that the rows object gets passed in with exactly the information that you want. And I think for the purposes of the demonstration of how to produce a data table with custom arbitrary data within it, that we have now met that bar. In practice, to make this recipe useful, I would probably filter out entries where the super type is java.lang.object because that's just not very interesting when you're interested in a class hierarchy report of your code. You'd have a whole lot of entries, one per type, saying that its parent was object, and that's just not very interesting. So I'd probably filter that out in a production version of this recipe, and I would add in implements relationships. I would also cover what interfaces were implemented and probably use an enum type, you know. You could use an enum to have, one of these. In order to record both class inheritance relationships and interface implementation. But we'll leave that as an exercise to you, the reader, if you want to kind of take this recipe to its logical conclusion. Okay, so that's kind of the gist of data tables. Now let's talk about scanning recipes. Now, as you're writing recipes, you may come up against a scenario where you are like, well, I want to reference information that comes from one file in a completely different file. And there's a lot of reasons you might want to do this. Things like, I only want to add, manipulate this piece of code if a particular dependency is present. I only want to remove this dependency if the symbols it provides are not available in code anywhere. Or you might want to do something like, I want to create a new source file. I want to add a source file to the project, and I need to know if it already exists or not. You can't just go adding it willy-nilly. It might already be there. And as we remember from last time, it's one of the first responsibilities of a recipe is to avoid making any bad changes. So let's get into the subject of scanning recipes. And what the recipe will work on here is append to release notes. A recipe that you could use to add or update the release notes. Say if you were making some change and you wanted to include in a release notes.md file in the repository something about that change, like, hey, we migrated to Java 21 in this release, for example. you could use a recipe like this to do it. So, so for this recipe to work, a recipe that's going to append to release notes, it has to handle the case where release notes doesn't already exist. Maybe this is the very first entry that is going to be put in the release notes, and this requirement that we look through all of the LSTs to determine whether any individual LST exists, and the notion that we're going to create it if it doesn't, means that we can't just be a regular recipe. Because a regular recipe, like assert equals to assert that, or class hierarchy, this visitor that you return from get visitor, it only ever sees one file at a time. And like I told you, recipes should be stateless. So this kind of has blinders on where it can only see one file at a time. And further, there is no mechanism in here for creating a new file, nor do you get any kind of notification of how far through the process you are. Like there's no like callback where you could say, after I've seen all the files once, then I want to do something. So if you find yourself asking these questions or having these problems, it's time to reach for the scanning recipe. And the scanning recipe is a lot like the regular recipe, but it has two additional capabilities in exchange for some additional complexity. So I'm going to just go ahead and define a type whose purpose will become clear momentarily. And I'll just say this is public static class accumulator. This class can be called anything. I tend to call it accumulator as a reference to its purpose of accumulating information as the recipe run proceeds. And scanning recipe wants to be parameterized with the type. And this can be anything. It's up to you what this type is. And this accumulator is going to be passed through all the phases of the scanning recipe, and it's going to be available to you to read and write information from as you see fit. So we'll add fields to this as we go. But for now, we will have IntelliJ implement the missing methods. And I'm going to put display name and description at the top, just because that feels neat to me. And now we see that it's also added a couple methods that a regular old recipe doesn't even have. Get initial value, get scanner, and I'm going to override two more. I'm going to override the generate method, and I'm going to override get visitor, but I'm not going to override the form of get visitor that these guys use, which accepts no arguments. I'm going to override the scanning recipe specific form of get visitor, which accepts this user defined accumulator type or recipe defined accumulator type. And so the way this works is that the recipe framework is going to call, or the recipe execution framework is going to call this get initial value method in order to get a value of type accumulator, such that it can then pass it through the rest the rest of this process. And after getting the initial value of the accumulator type, there's an entire phase of recipe execution that regular recipes don't know about at all and don't get to participate in. And that is the scanning phase. When every recipe, and every scanning recipe at least, gets to look through all of the source files and apply a visitor to them and not make any edits. This scanning recipe can extract information from them, but if you try to change one of the source files in here, those changes will be harmlessly thrown away. This isn't the editing phase, this is the scanning phase. So this is where you get to look through all of the files and record any information that you're interested in from those files into your accumulator type. So what we're interested in primarily at the moment is whether or not the README already exists. And then we are going to, and then between the scanning phase and the editing phase, there's an optional generate step where any new files you want the recipe to produce can be produced, and these files will be written out to disk. And finally, there's the visitor phase or the edit phase, which is exactly like the edit phase from a regular recipe, except that you still have this accumulator object available, so you can reference any information that you collected in the scanning phase. So now that we've kind of talked about the enhanced life cycle that scanning recipes participate in and their additional capabilities, let's get down to implementing this one. So append to release notes, add a message to the end of a release.md file, creates release md at the repository root if it does not already exist. Cool. And since we want to be able to customize the message, we need to make a parameter on here. So we'll just call you string message. And thanks to our Lombok value annotation, the constructor for append to release notes that gets generated will have a message parameter. And since this is an option to an OpenRewrite recipe, we need to import the org.openrewrite.option annotation in order to provide the relevant metadata about what this guy is and does. Yeah, and so you could, include a message like this to your Markdown file. Yeah, and let's go ahead and before we get concern ourselves with implementing this further, let's go ahead and create a test that's going to exercise it a little bit. So we can create our append to release nodes test. And just like usual, we're going to implement rewrite test. We'll override our defaults method. We'll say we're going to run new append to release notes, and now it requires a parameter, and we're going to add hello world to our release notes. Good old classic program. Okay. Create new release notes, and here we'll make two tests. One that covers when the release notes do not already exist, and one that covers when they do. So you may be asking yourself, how do I assert the creation of a file? And you do that like this. You specify that the before value is null and the after value is not null. And you should specify, and this is within the assertion itself, not within the rewrite run invocation. We can check that the path that this file should have should be release.md. Okay, and now we can quickly create the append release notes to make sure that this also works. And we'll just say release notes. And we'll do this GitHub style and say what's changed. And we'll say that after running the recipe, this release.md should have these contents. Okay, so now we've covered both of the kind of basic situations, and let's implement that. Okay, so for this recipe, yeah, get initial value is pretty simple to implement. Oops. Let's return our new accumulator type. Get scanner, we're going to return a recipe, or not return a recipe, we're going to return a visitor, same as we would elsewhere. Now, a release nodes.md file is going to be parsed as plain text, so we can use a plain text visitor. And the main thing we're interested in here is, does it already exist? So we could say visit text. A plain text source file, as you might imagine, has the incredibly simple plain text LST, which is just kind of the usual LST element accoutrement around a string. So what we are going to do is check if we're going to check if this guy has the source path, and GitHub Copilot is not quite right about what I want to do here. So if the source path, well, we'll invert this so that release.empty equals text get source path to string. Then we will say ack dot, oh, we want to set a field to true on our file, so or on our accumulator. It already exists. So we will set on our accumulator true. So that's all our scanner has to do. It just looks through the plain text files in the project, checks if one has the path release.md, and if it does, we note already exists equals true. Okay, so now this is what we need to know in the generate step to decide whether or not we want to create this source file. And so we can say if and the super version of this method just returns an empty list, since by default we're not going to do anything. So if it already exists, we'll just return an empty list. And if it doesn't already exist, we need to return a source file representing it. And if you are in a recipe and find yourself needing to produce a new LST or a new LST element, and something like Java template is for any reason not suitable, you can just create a parser. And so in this case, we'll get a plain text parser, and we'll tell it to parse the string. We'll tell it to parse the empty string. And this guy, actually, the parse method returns a stream, in this case of a single source file. So we need to set its path. And you must set the path or it won't know where to put it. Yeah. So here we're going to parse the empty string into a source file. We're going to set its path to release.md, and we're going to leave it up to the edit phase to actually do the appending to it, so that the edit phase can look the same whether or not the file already exists or was freshly created. So now we're in the edit phase, and we can say return new plain text visitor. And GitHub Copilot is pretty good at figuring out that I want to override visit text. I want to check the path. And I think I will just do one more thing and say, let's do just one new line, and we'll say, and text get text that already contains the message. We don't want to add it. Oops, not trying to get too deep into this. Cool. So let's see if I did that right. This should be basically the full implementation for our visitor. Let's see if these tests will pass. Yep. So if we're creating a new release notes, we do get the result we want, and it does have the path we want. And if we are appending to an existing file, every input should be parsed into a source file. What? Oh, I said Java. That's why it doesn't work. I'm trying to produce plain text files, and for some reason, just purely out of habit, I suppose, I am parsing them as Java. So what I want here is actually this this text assertion from source specs, not the Java assertion, because these obviously are not not Java source files we're working with, and it was helpfully letting me know that this guy was the Java parser could not make any sense of this. Okay, now that we're making an assertion about that this is text, this passes as it is supposed to. And I have learned something about our test framework, that the Java assertion does not assert that when a file is created that it is of type Java, which feels like an oversight that I should go correct. But there you go. That is the basics of scanning recipes, as well as the basics of data tables. And you should now feel equipped to go out and create these for yourself. And we have some documentation on these things as well under in the OpenRewrite documentation, where'd my browser window go? Yep, there it is. So there's this getting started with data tables that you can check out that 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 describes that feature a little bit. And there's also some information on scanning recipes. So I encourage you to check this out if you want to learn about these subjects in more detail or refresh your memory as you're coming back to this later. Okay, so that is about all the time we have for today. IntelliJ tip, pressing Control-Shift-T on the class will ask her to test. Tim, that is a great tip. How did I never know that you could do that? Control-Shift-T. Well, I probably already have a test for that one. But anyway, thank you, Tim. Appreciate that tip. And thank all of you for coming. I hope you felt that this is a valuable use of your time, and I look forward to seeing the great recipes that you will contribute to open source, or at least make your own internal private code better with. I've been Sam Snyder. Goodbye for now. Oh, and if you wanted to learn more about the data visualization topic, next week's OpenRewrite Community Office Hours on Wednesday, we'll have Kyle Scully on, who has implemented a lot of cool front end stuff like that. So check it out. Okay, thanks a lot. Have a great weekend, everyone.